Good evening, everyone, and welcome to our newest and fresh lecture. This is Electrostatics lecture number 13. And in the previous lecture, we were dealing with the electrostatic potential and electrostatic potential energy. We had seen the electrostatic potential created by a point charge. We had seen that if it is a positive charge, it creates positive potential plus kq by r. If it is a negative charge, it creates negative potential minus kq by r. We'd also seen if you have a number of charges, then how do you calculate the potential at any point? We calculate the potential at any point by finding out the potential due to individual charges and simply adding them up, because the best thing about potential is that it is a scalar quantity. We can just add them up. We'd also seen the potential created by one positive and one negative charge, and we have seen that on line or this one plane, the potential remains same. Equipotential surface, we'll come to equipotential surface when time comes. And then we had seen some theoretical questions on electric field and electric potential. Electric field is zero. That means the potential can be zero, it may not be zero. If potential is zero, it means that electric field may be zero, it may not be zero. But if electric field is zero, the potential must be constant. Do we remember all of those? Yes or no? Now, since we have seen the potential due to a single point charge, it is now time for us to understand the potential energy of 2-point charges. Remember, a single point charge in the universe, it cannot have potential energy. To have potential energy, we must have electric field. Now, this electric field has to be created by someone else. So if there is only one charge in the entire universe, which is not possible, then there is no potential energy. But if you have even 2-point charges in the entire universe, you will have the concept of electrostatic potential energy, and that is the concept that we are going to begin our discussion with. Electrostatic PE of 2-point charges. And there are a varied number of questions that can be asked here, so this might take time. I will try to finish it in this class. Let's see how things go. There are a certain number of questions that we have to do. If we can do them, well, good. If can't, then we will have to extend it to the next class. Anyway, the electrostatic potential energy of 2-point charges. Now, I will again not go into the derivation part of it because we are not going to get much out of it. This is the point charge. Placed somewhere else. Now, how this potential energy of this system or this charge comes. Now, this point charge is placed here. What we assume is before placing it here, this point charge was at infinity. It was as infinity, and someone, electrostatic force or someone, went there and bought this charge and put it here. Now, when this charge was brought and put here, there was no electric field because there was no other charge in the entire universe. So to bring this charge from infinity and put it at this point, there was no work done because there was no electrostatic field. Do we understand this? So this charge has been brought and put here. No work has been done because there was no one else in the universe. But now, there is one charge present in this universe. And this is this point charge. Now, if I have to bring another point charge from infinity and put it here, some work has to be done. Some work can be done because now there is electrostatic field created by this point charge. So electrostatic field or someone has done the work and put another charge. Let me call this first charge as Q1 and let me call the second charge as Q2. So work has to be done to bring this second charge from infinity to this point. That work done, because it is work done against a conservative force, this work done is stored in the form of energy in this 2-point charge system, and that is known as the potential energy or interaction energy of these 2-point charges. If these 2-point charges are separated by a distance of r, what is the electrostatic potential energy of this system? The electrostatic potential energy of this system is given by this formula, K Q1 Q2 by R. K Q1 Q2 by R. Now this electrostatic potential energy can also be called as mutual energy because it is because of the mutual interaction. Now this mutual electrostatic potential energy can be positive, can be negative, it can also be zero. It is zero at infinity anyways. What decides whether it is positive or negative? It could be positive. This energy, interactive energy, could be positive, or this could be negative. When will it be positive and when will it be negative? Remember, energy is a scalar quantity. Yes. When is this energy positive and when is this energy negative? It does not take rocket science to understand this. We're not studying rocket science, we are studying electrostatics. Yes. When is this energy going to be positive and when is this energy going to be negative?
Positive when both charges are positive, or negative. Negative when one of the charges opposites.
So basically, if they are of the same sign, this energy is positive. Oops, wrong color. I hate wrong colors. If both the charges are of same sign, both are positive or both are negative, this energy would be positive. Negative into negative is positive. Positive into positive is positive. If they are of opposite sign, this energy is negative. That's it. That is electrostatic potential energy of a system of 2-point charge. You need at least two charges, 2-point charges to have this energy. So far, so good. Now, if you have what? If you have more than 2-point charges, see, if you have more than 2-point charges, then how will you find out the electrostatic potential energy of that system, which has more than 2-point charges? If you have more than 2-point charges, then how will you find out the electrostatic potential energy, or this type of energy is known as electrostatic interaction energy? How will you find the electrostatic interaction energy of more than 2-point charges? Hmm? How will you find out the potential energy of a system of, let us say, 3 or 4 or 5-point charges?
Sir, by superpositions.
How will you superimpose? What are you going to superimpose or superpose? So you will break them up into pairs of 2 each. You will find the energy of one
From
pair.
one charge to same point and another charge to the same point, adding.
Okay. So basically, if you have more than 2-point charges, what you are going to do, if you are going to find out the potential energy of one pair, find out the potential energy of other pair, third pair, fourth pair, and so on, and you are going to simply add them. That is how you find out the potential energy of more than 2-point charges. To understand this concept, let us solve a question. So it's nothing better than to understand a concept by solving a question. So what is the question that we are going to solve? Let us say that you have an equilateral triangle, and this equilateral triangle consists of 3-point charges, plus q, and minus q. The length of this, the side length of this equilateral triangle is, let's say, A. The question is very simple. What is the interaction energy or the potential energy or the electrostatic potential energy of the system? I'll give you 2 minutes to do it. Do simple things, nothing complicated.
Minus k. Sir,
2k square by a, sir.
minus
Minus
q square by a.
k square by a. It looks good. How did you get it? It's pretty simple. It's just like simple addition and subtraction and simple multiplication. There is no hidden agendas here. It's very simple. You find out the energy of one pair. You find out the energy of the next pair. You find out the energy of the next pair, and you are done. Anyone understands this? You have to just see how many pairs are there. I'll give you 1 more minute. I see some students still working out the problem, so I must wait. I give them 1 more minute to gather their thoughts together. So, done, everyone?
Yes, sir.
So how are we going to do this? Okay, I've lost contact. Anyways, how are we going to do this? We are going to break them into pairs. This is pair number 1. This is pair number 2. And this is pair number 3. There are 3 pairs here. To find the energy of the first pair, what is the energy of the first pair? K Q square by A square. You find the energy of the next pair. What is the energy of next pair? K minus Q square by not A square but A. See, I made a mistake. By A. You find out the energy of the third pair. There are 3 pairs here. Third pair minus K Q square by A. We are finding the energies of the pairs. 3 pairs are there. 3C2. I hope you understand the meaning of 3C2. Yes or no? Number of pairs.
Yes, sir.
3 combination 2. 3C2. So there will be 3 pairs. You find out the energy of all the 3 pairs. You simply add them and you land up with your answer minus KQ square by A. So that is the interaction energy or the electrostatic interaction energy or the electrostatic potential energy of this system. Everyone understands this? Can I raise hands from everyone? Boys and girls? Boys in the other class? You understand this? Okay, this is as simple as it gets. Let us do one more simple problem. Then we will try to get into somewhat more complications here. Now I have a square. Let me make it symmetric. So this is plus Q. This is minus Q. Arrangement could be anywhere like this. And this is minus Q. The edge length of this square, let us say, is A. The edge length of this square is A. Again, the same question. Find the potential energy, electrostatic potential energy, electrostatic interaction energy of this system. You have 2 minutes to do it.
Sir,
Yes, beta.
minus 4kq square by A.
minus 4 kq square by A. Is this the only answer, or we are having more controversies? Different answers. So I've got one answer, minus 4 kq square by A. Do we have anyone who can contest this answer, or are we getting the same answers? Democratic answer. Democracy wins in India.
minus 3k squared by A.
So democracy is not winning because another candidate has stood. The answer is minus 3kq square by A. And any more candidates? Who is going to win or who is going to contest the election?
kq square by root 2a.
So we have one more contestant, kq square by root 2a. And the good news is, what is the good news? All of these contestants are losing because all of them are wrong. Democracy does not win in physics. Only logic and physical laws win in physics. Democracy cannot win.
Sir,
Yes.
kq square by A into root 2 minus 4.
This answer looks promising. This is a promising candidate, and this is, in fact, if the signs are correct, this is the correct answer. So you see, democracy doesn't always win, and you must not rely on democracy in physics. Democracy only works in the elections in India or wherever democracy exists. It's no democracy that all of the scientists start saying that this is correct. That does not mean that it is correct. Even one of those scientists can change the entire physics. That is what Einstein did when he proposed his general theory of relativity. He shut apart everything that was prevalent at that time. Newton, everything just went to pieces because it was Einstein who was there. Physics wins. Let us look at the number of pairs. Oops, wrong color. I hate wrong colors. Pair number 1, pair number 2, pair number 3, pair number 4. Now each pair is separated by a distance of A, and each pair consists of one positive and one negative. So, I mean, a third standard student will tell us what is the energy of this system. And the energy of this system is minus kq square by A. And that is the correct answer. How many of you got this? That is the answer, minus kq square by A. How many of you got this answer? No one? Everyone is looking at each other. No one got this answer? That is the answer, my dear friends, minus kq square by A. How many of you got it? Someone got minus 3?
Sir,
Yes.
kq square by A into 1 by root 2 minus 4, sir.
Sorry, minus 4. Minus 4 kq square by A. That I was wrong. Minus kq square by 4A. The problem here is I have not taken all. There are two opposite pairs. Dung, 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 dung. This is pair number 5. 4C.
Sir,
This is pair number 5, and this is pair number 6. So there are 6 pairs.
Sir.
4 pairs of plus q minus q, and 2 pairs of plus q and minus q separated by a distance of root 2a. The energy is same, so the total energy of this system is plus 2 kq square by root 2a. That is the answer of this. Do we understand this? Yes or no?
sir,
Yes.
Sir,
we got the same answer, sir.
Congratulations. You win. So that is how you must find out the energy of any system, by looking at the number of pairs, looking at the distance of the pairs, multiplying it and dividing it by the correct distance. That is how you find out the energy of any system. Have we got this? So now you can make a variety of questions. The point charges could be put around a circle and this and that. At the end, this is what you got to do. Now, this may not sound as a very enterprising question, but the question in a JEE could be asked in a different way. The question could be this way. What is the work done in assembling this system? What is the work done in dismantling this system? Again, in this work done in assembling and dismantling, there are also two things that can come. Work done in assembling by electrostatic force and work done in assembling by external force. So you have to be careful which work done is asked and how do you understand that work done. So how do you find out the work done in assembling this system? And I just try to explain it. Now, work done in assembling by electrostatic force. Work done in assembling this system by electrostatic force. How will I find it out? What do you mean by assembling this system, first of all? Assembling this system means all of these charges in the beginning were at infinity. One by one, charges come and they are placed at these points. Do you understand this? So work done in assembling this system is, if I write it in symbols, it will be work done in moving all these charges from infinity and placing it in this configuration. If I call this configuration as the final configuration, and when I say final configuration is the configuration of this system. This is the, oops. This is the final configuration. Let me call it as F. So work done in moving all these charges from infinity, they were initially at infinity, to this final configuration by the electrostatic force. So how do you get this? Work done from A to B by electrostatic force is UA minus UB. So it becomes U infinity minus U final. Do we understand this? How I written this? Yes or no? You understand this? This is how I, from the previous way of writing work done by the electrostatic force. See here. Here. UA minus UB, initial minus final, is work done from A to B, initial minus final, initial to final. Do you understand this?
Yes, sir.
Yes, sir.
A point is infinity and B point is the final configuration. A point is infinity and B point is the final configuration. And therefore, now remember, when the system is at infinity, the energy when all the charges are at infinite distance from each other is zero. So this work done by the electrostatic force in assembling this system is nothing but negative of U final, or you can say is negative of U system. Do we understand this, or this has gone above our saying bye bye?
Understood, sir.
Everyone understands this? Now someone was asking me a question where bricks were kept on top of each other. This is keeping the bricks. Instead of bricks, I am putting charges. You understand this? Same question. Question is same. Exactly same. There it was work done by gravity. Here it is work done by electrostatic force. Do we understand this? Now once you understand this, then the rest of the four heroes can be understood on this configuration. Work done in assembling this system by external forces. that will be equal to negative of this work. So that will become the energy of the system. Remember, here I have assumed the change in kinetic energy is 0. Whenever we talk about work done by external forces, work done by external forces will be negative of work done by conservative forces if the change in kinetic energy is 0. Do we understand this work energy theorem? We understand this, yes or no?
Yes, sir.
Then you can write the reverse of this. Work done in dismantling this system. So work done in dismantling this system by the electrostatic forces will be negative of the first work. So it will be U of the system. Work done in dismantling this system by the external forces will be minus U of the system. Everyone understands this? Yes or no? You understand this? How I have done this?
Yes, sir.
So just remember, just be careful about this positive and negative signs, because in JEE, if they give you an option, they might give you the positive sign. They might also give you the negative sign. Do we understand this? Everyone understood this? Yes or no?
Yes, sir.
Everyone has noted this down?
Yes, sir.
Okay. That finishes this part of the question. Now, I could have asked the same question here. For example, I could have asked in this question, what is the work done in assembling this system by the electrostatic force? And what is the answer? Work done in assembling this system by the electrostatic force.
KQ square by A.
KQ square by A. Work done in dismantling this system by the electrostatic force will be minus KQ square by A. We understand this, everyone?
Yes, sir.
Now we come to the next aspect of the question. Remember, all these are questions, and every question has the potential of being asked in the exam. I bring our thought to the next variety of question. And the next variety of question is like this, question number 3, if I am correct. Now, as you can understand, the question remains same. So basically, in the previous question, what I gave you was the final configuration, how they were placed. Now, in this question, I am going under a process of how they were placed. Now, 3 charges are already here. I have brought these 3 charges from infinity and placed it here. Now I have to get the 4th charge. So the 4th charge is here, plus Q charge is at infinity, lying there. Someone has to go and bring it. Hey, come, you have to come in the system. So someone is going and bringing it, doing. It can come in any path. I'm just making it theoretical. It can come in any path. So ding, 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 ding. It has come and it has been placed here. Let me now make it blue. Let me now make it black. Now this charge was at infinity and it has been brought and placed here. The side length is A, remember that. Now I ask you this question, what is the work done? The electrostatic force in bringing this charge from infinity and placing it here. Work done by electrostatic force in bringing this charge from infinity and placing it here. You understand the question? Yes or no? You understand the question? Yes or no?
Yes, sir.
Yes, sir.
You have to solve it.
Sir,
Yes.
minus of 2kq square by a into minus 2 plus 1 by root 2.
Let me call this position as A. So basically what you are telling me is work done to bring the charge from infinity and placing it at the point A by the electrostatic forces. Yes, what is the answer, beta, that you got? You said the answer, right?
Four kq square by a minus 2kq square by root 2a.
KQ square by A
4kq
minus
square.
KQ square by A
4kq square by a, sir.
4KQ square by A minus
2kq square by root 2a.
2KQ square by root 2A. This is the work done in bringing this charge, the red charge, from infinity and placing it at point A. What was the work done in assembling this system? It was the same, now. So you bring all the four charges or you bring only one charge, the work done is same. Is
Sir,
it possible? No.
sir,
Yes.
kq square by a into 2 minus 1 by r square.
R square, that is dimensionally wrong. Cannot be R square.
No, 1 by root 2. kq square by a into 2 minus 1 by root 2.
KQ square by A into
2 minus
2 minus
1 by root 2.
1 by root 2. This looks promising. How did you get this? This looks promising. How did you get this?
UA is equals to U assemble is equals to
What happened? Okay. Let me tell you how it is to be done. Now remember what I have is there is an initial system and there is a final system. In the first question, initially there was nothing. No charges were there. And finally, all the four charges were there. Here, if I look at the initial system, my initial system has these three charges. Yes or no? This is my initial system. Do we understand my initial system?
Sir,
This is the initial system. What is my final system? My final system is the red system. My final system is the red system. This is my final system, and that is what you had to do. You had to find out, instead of writing it as U infinity to A, you could have written it as U initial to U final. Do we understand this?
yes, sir.
So work done in changing the system from initial configuration to the final configuration would be initial energy in the initial configuration minus energy in the final configuration. Do we understand this?
Yes, sir.
That is what you had to do. So you find out the initial energy, you find out the final energy, and then you subtract. Okay? Do we get this?
sir.
So this is one way of doing it. So what is the initial energy? The initial energy is the blue energy. What is the blue energy? I have two pairs of plus q minus q. So it is minus 2 k q square by a, and I have one pair of minus q and minus q. I have one pair of minus q and minus q. So that becomes k q square by root 2a. This is my final energy. We understand this, yes or no, for the blue configuration?
Yes, sir.
Now I subtract the final energy of the final configuration, which we have already calculated. So that is equal to minus 4. That is minus 4 kq square by a plus 2 kq square by root 2a. You subtract these two and you get your answers. Am I clear with this concept? Yes or no?
Clear, sir.
This is tariqa number 1 of doing it. This is way number 1 of doing it. Way number 1 of doing it. In this way, you have to find out the initial energy of the system. You have to find out the final energy of the system, subtract final from the initial ui minus uf, and you get the work done by the electrostatic force. What is the answer that you are going to get? Can anyone tell me the answer?
KQ square by A into 2 minus 1 by root 2.
That is the answer that you will get. You just subtract and you will get the answer. So the answer will be 2kq square by A minus kq square by root 2a. This is the first way of doing it. We understand this first way?
Yes, sir.
Now let us see. Remember, JEE is a test of your speed. You have to do it faster. And the faster you do it, faster you can move on to the next question and you can have an edge over the other competitor. Now, if I just use some smart work, I don't have to do all this. Now, I look at the initial system and I look at the final system. Initial system had 3 charges. The final system had 4 charges. Now, I just see bringing this charge, this green charge, bringing this charge actually increases 3 pairs. Bringing this new charge increases 3 pairs. What are those 3 pairs which increase? Pair number 1, pair number 2, and pair number 3. These are the 3 pairs that increase. The rest 3 are still same. So why I calculate that first one? You just find out what is the what are the number of pairs that has increased and take the negative of that. That will be your answer. Because ui minus uf is simply equal to minus how many extra pairs are created. Do we understand this?
Yes, sir.
So I just find out the energy of these 3 pairs and take minus, and we are done. That would be tariqa number 2. What I have done in this way, I've just used some smart work. I know that these 3 pairs, these 3 blue pairs are common to both the configurations. They are going to get cancelled. I only have to be concerned with these 3 new pairs that I have created. Just find out the energy of these 3 new pairs and take the negative of it. We understand this?
Yes, sir.
Yes, sir.
This is method number 2 of doing the same thing faster. Find out the energy of 3 pairs. Take the negative of it. There is one more way of doing it, the third way of doing it, which is, I think, the fastest. What is the fastest? You know the way number 1, you know way number 2. Now I'm telling you way number 3. So now what do I do? Okay. So what do I do now? I see that there are 3 charges and there is a point there. And I have to bring this 4 charge from infinity and place it at that point. So basically, now I just concentrate on that charge which is moving, nothing else. So now I start thinking, okay, I have to find out the work done by this. So and now I write the equation like this. Work done in moving this charge. Only I'm concerned with one charge. From infinity, work done in moving this charge from infinity to, let us say, this point A will be equal to energy of this charge at infinity minus energy of this charge when it is brought at point A, because this is the only charge that is moving. So far, so good. So that will be equal to, if I multiply this charge by the potential difference between infinity and point A, that is how potential difference is defined. Energy, difference in energy is charge multiplied by potential difference. Yes or no?
Yes, sir.
Everyone understands this, what I've written here?
Yes, sir.
Now, potential created by these three blue charges at infinity is 0, yes or no? Because
Yes,
they can't
sir.
be. At infinity, the potential is 0. That is what we have taken. So basically, I have to find the potential at point A, take the negative of it, and multiply it by the charge. So my third way, which is the fastest way, according to me, plus Q, or I take the minus sign out. So instead of plus Q, I will write it as minus Q multiplied by the potential of point A. What is the potential of point A? What is the potential created by point A? Minus 2Q into K by A. This is the potential created by the two negative charge plus potential created by the positive charge. K Q by root 2A. And that is your answer. Do we understand it? Though this has gone above, they're saying, why, sir? Why? Gone. This is gone.
Understood, sir.
No way this is coming back to us. This is gone. Doi. So I've told you all the three ways. You just have to think which is the fastest one to do. Everyone understood this? I'll give you 2 minutes. If you have any doubts, please ask. Yeah.
Completed, sir.
Got this, everyone? Yes or no?
Sir.
Yes, sir, or no, sir?
Yes, sir.
Everyone, sir? Shall I now put some interesting questions?
Yes,
Huh?
sir.
Yes, sir.
Okay. Question number 4. There is a plus Q charge placed here, sitting and chilling out. This is fixed. This is fixed. Then there is this gentleman point A. Then there is a small charge minus Q placed here at infinity. At rest. Chilling out at infinity like you are. Now, what happens to this minus Q charge? This plus Q charge cannot move, so it is fixed. What happens to this minus Q charge? It will come towards this, yes or no? Huh?
Sir.
Sir.
It will come towards this. You understand this?
Yes, sir.
Why it is coming? Because electrostatic force is pulling it. Come. So it is at rest at point at infinity. But when it comes to this point, and now this gentleman has come here and he is smiling. I am here. He is moving with some velocity v. Yes or no?
Yes, sir.
Find out the velocity v. हाँ ये कैसे होगा? Sir, you teach something and you give question पता नहीं from something. You have to find out the velocity v of this charge at point A. You have 2 minutes to give me the answer and stay happy. The time starts now, my dear friends. Good or bad? That I don't know. If you can't do, let me know so that I can show you my skills.
Sir,
Yes.
is the distance, sir?
Oh, bad mistake. R is the distance. Sorry. Bad mistake. R is the distance. R is the distance, my dear friends. R is the distance. Tan, dig, 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 dig. With background music. Let's see who can give the answer with background music. Any hope of getting answer? Yes, sir or no, sir? Better I go, sir. Eh? Or shall I do one? Then you will be able to replicate the question. Eh? Say something. This is the question where two topics mix, and this is the favorite of JEE Advanced. At one point in time, these type of questions were favorite. Now they also can come when they mix one topic with the other topic. Here, which two topics have been mixed? Here, your mechanics is mixed with electrostatics. Mechanics, electrostatics, they sound same as well. And that is how difficult problems can be made, my dear friends. You have 2 minutes left on the clock to show your talents. Else I will show mine and I'll praise myself, see how good I am. 42-year-old fellow solving problems. 17-year-old cannot solve. Shameful.
Sir,
Yes, I have an answer.
square root of 2k q square by rm.
Looks promising. That I think is the correct answer. It looks promising and it looks correct as well. Well done. See, if you give it a sincere try, you can achieve the whatever is unachievable. And there was what should I call a small share or what that saying or whatever you call it in Hindi. I don't know how many of you understand Hindi. So that share went up like this. Understand शेर ना शायरी शेरो शायरी something of that nature. So this it was like this. कौन कहता है कि आसमान में छेद नहीं होता? Who says that you cannot plug a hole in the sky? कौन कहता है कि आसमान में छेद नहीं होता? एक पत्थर तो तबीयत से उछालो मेरे भाई. So you throw at least one stone in the sky and try to create a hole in the sky. Even a hole in the sky can be created if you start throwing stones. So you see, and creating a hole in the sky with stone is way tougher than this simple question. So if you try hard enough and keep on trying, one day you will end up with the correct answer. Yes, how did you get the answer? I have praised you so much. I have even not checked whether the answer is correct or not. Yes, how did you do it, bacha?
Potential energy equals to kinetic energy.
Potential energy equal to kinetic energy. That's absolutely correct. There's no reason why this should not be correct. Why is potential energy equal to kinetic energy? Though your concept is still a bit dancing, but it is a bit dicey. But I must appreciate that you applied it correctly, and everything came together. And when everything comes together, you know, things happen. Okay, how to do it? I will tell you a number of ways, and then you choose which one you think is the best one to solve it. Way number one, the blue way. Now, the only force acting here is the electrostatic force. Yes or no? And this electrostatic force
Yes,
is
sir.
the only force. So remember, I am going to apply WET. What is this WET? Work energy theorem. Work energy theorem. And this work energy theorem says that work done by all forces is equal to change in kinetic energy. Do we understand this?
Yes, sir.
Now, to find out the work done by all forces, there is only one force, which is electrostatic force. This electrostatic force is doing work in bringing this charge from infinity and placing it at point A by the electrostatic force. Do you understand what I've written here? That must be equal to the change in kinetic energy. Change in kinetic energy is final kinetic energy minus initial kinetic energy, which is 0. Now to find out this green thing, now this blue thing, because it is blue, this blue thing, work done from infinity to A, I can just, you don't need to integrate, you don't need to differentiate. What I'm going to do is I just find out energy of this system at infinity and subtract the energy of this system at point A. And I'm not going to get lucky, because whatever I get will be the correct answer. Energy of the system at infinity minus energy of the system at point A, that must be equal to half mv square. Do we understand this? Yes or no?
Yes, sir.
What is the energy of the system at infinity? The energy of the system when the charge is at infinity is 0. Minus C is not potential energy is equal to kinetic energy, because it's negative. It's negative here. You have to understand why it is negative here. So it's negative of the potential energy when the two charges are at a distance of r apart. So it becomes minus of minus k q square by r. Do we understand this?
Yes, sir.
That must be equal to half mv square. From there you can find out the velocity of this particle. Do we understand this? Yes or no?
Yes, sir.
Yes, sir.
Tarika number 2. I will apply the same work energy theorem. Step number 1 is same. Step number 2 is same. Step number 3 is same. But to find out u infinity minus ua, what do? I multiply minus q, which is the charge, v infinity minus va. Do we understand this? Where I've changed the steps?
Sir.
That must be equal to half mv squared. So instead of finding the initial initial potential energy and final potential energy, I find the potential difference and multiply it by minus q, because minus q is the charge which is moving. We understand this? That is tarika number 2, which is derived from tarika number 1. The third tarika is lock me, our favorite lock me. What is this lock me?
Conservation of mechanical energy.
एक पत्थर तो तबीयत से उछालो मेरे भाई. Lock me. I apply lock me. So energy, whatever energy it had at infinity, total energy, mechanical energy at infinity must be equal to mechanical energy at point A. We understand this? Why I can apply lock me? Because the only force working here is the conservative force, which is electrostatic force. So energy must be conserved. We understand you. This is gone above by saying bye bye. Bye bye.
Understand, sir?
What is the total mechanical energy of the system when the system is at infinity? It is zero, because potential energy is zero and kinetic energy is zero. Yes or no?
Yes, sir.
What is the total mechanical energy of the system when the charge is at a distance q? It has a kinetic energy half mv square, and the system has potential energy minus k q square by r, and I land up with the same answer. Do we understand this, or this has gone above or at saying bye, bye bye, bye bye, and bye bye?
Understood, sir.
Everyone understood it? Yes or no?
Yes, sir.
Pakka?
Pakka, sir.
Then comes the cousin brother of this question. Are we ready for the cousin brother? Or the twin brother of this question? The cousin brother will be the third one. Can I bring out the cousin brother?
Yes, sir.
No, the twin brother, not the cousin. See, I'm getting confused between cousins and twins. Cousins are cousins, twins are twins. So here comes the twin brother of this. So here is the twin brother. And that twin brother is like this. Wrong color. I hate wrong colors. The twin brother is like this. This charge, the plus q charge, is chilling out at infinity, and it is at rest. Now I am doing the question from infinity, but this question could be done at a distance apart. So I will try to do it in the next question. This plus q is chilling out at infinity. So is the twin brother minus q chilling out at infinity. When they're chilling out at infinity, it is at rest. Both of them have the same mass as well. Let us take the mass as same. Both are chilling out. And all of a sudden they realize that, oh, they are charges. And here we are doing this question for electrostatics. We are not doing for gravitation. Same question could be made in gravitation. Now here we are assuming that the gravitational force is very, very weak. In fact, compared to electrostatic, gravitational force is really very weak. So we don't have to consider gravitational forces here. We only have to consider electrostatic forces here. Do we understand this?
Yes,
All
sir.
of a sudden they realize that they are infinity, and some force is pulling them together. What force is bringing them together? It's not
Electrostatic
the
force.
electrostatic force. So my twin brother is coming, my twin brother is coming, my twin brother is coming. And this gentleman comes here, and this gentleman comes here. The distance between them is r. They must be moving with some velocity. Yes or no? Yes or no?
Yes, sir.
The first question is, will the velocities be same or different? Are the velocities going to be same or different? Huh?
Same, sir.
Same, sir. Same, sir. So this is moving with a velocity v. This gentleman is also moving with a velocity v, and you have to repeat the same question again. Find out the velocities of these twin brothers who are supposed to meet. They are very eager to meet. They have come from infinity. बहुत दूर से आया हूँ. So they have come from literally infinity for this question. They have done so much for us for this question. So it's our job to finish the question. When I say finish the question, that means to solve the question. Do not tear your book apart. Okay, I finished the question. See, chalo. What is the velocity of both the particles when the distance between them is r? You have exactly 2 minutes to do it. Huh? Any hope? No hope, sir. Hope is gone. What hope, sir? You teach something and you give question from something. What is this? Not fair. Anyone with anything that looks like an answer, sounds like an answer, feels like an answer, please come up. Everyone is looking at each other's faces. Remember, answers are not in each other's faces. Answers you will get only by doing the question and not looking at each other's faces. Because we are still to develop a technology where answers are on each other's faces, and you look at each other's faces. I see your face and I got the answer. It's not going to happen. Yes, my dear friends. Anyone? Yes, my dear friends. Huh? Shall I do it? Anyone with anything that looks like an answer? No one?
2 root kq square by mr.
The same answer as the previous one? It can't be same, no, bacha? The question, this one was different. This has to be somewhat different, no? Okay. So here comes my turn of solving it. Now I can use any one of these ways. I will use the one which I love the most. And that is what? Logme. Logme is known as the daughter theorem. And the daughter theorem can work while I use the mother theorem. Work energy theorem is known as the mother theorem. It's the mother that gives birth to this daughter. And this daughter is good enough to solve this question. So why disturb the mother? So what does this daughter theorem tell us? It tells us that the energy of this system at why I'm writing UE. The total mechanical energy of this system will remain conserved because conservative forces are working. So the total mechanical energy at the initial point infinity shall be equal to the total mechanical energy at the final point or final configuration A. Remember, I am talking about the configuration. This is the final configuration. The total mechanical energy when they are at infinity is 0 because potential energy is 0, kinetic energy 0, everyone is chilling out, doing nothing. Now when they come at a distance, yes,
V square is equal to 2kq square by mv.
same answer, no Fito. Change nothing in this. This gentleman charge is also moving. Nah, sir, you've forgotten this, nah, sir. So the mechanical energy when both the charges are infinity is 0. Now when they come at this point, both are moving. So half mv square for the first charge plus half mv square for the second charge minus kq square by r, that must be equal to 0. You solve this, you get your answer and you stay happy. So the answer in this case will be under root of kq square by mr. Do we understand this? Or bye-bye? Bye-bye? I'm going. I had enough of this. I'm bye-bye. Bye-bye? Oh, we have understood this.
Understood, sir.
Okay? Chalo, then comes the cousin brother of this question. This has cousin brother as well. And now cousin brother, I will not bring charges from infinity because we have done enough of infinity. Now this cousin brother starts like this. Question number 3, the cousin of this.
Sevens, can you please place previous side?
Yeah, beta?
Place previous slide.
You are not able to do this? What was wrong? What do you want to see? See?
Completed, sir.
Okay, then comes the cousin brother of this. In this cousin brother, this is plus Q charge. This is also plus Q charge. Chalo, one thing is same. Now I place them at a distance r apart. Both of them can move. Both of them can move now. What will happen to them now? Both of them can move. There is no gravity, nothing. Both of them can move. So what will happen? Will they move towards or will they move away?
Repel.
Away.
Away. You see? So now they have moved away, cousins. And now this charge is here, plus Q. And this charge is here. I'm not bringing infinity. Let me change the color of this so that you understand. Now this charge finally is here and this charge finally is here. The distance between them becomes twice. Oops, what I'm writing. The distance becomes twice of the original distance. Now since this is cousin brother, they don't have the same masses. Mass of this one, wrong color. I hate wrong colors. Okay, I hate wrong color. So mass of this is M1 and mass of this is M2. Now they have different masses because they are not twins, they are cousins. They have different masses, M1 and M2. This will move here. Let me call this velocity as V. This will move here. Let me call this velocity V. Are both the velocities going to be same?
No, sir.
No, sir. So I call this as V1 and I call this as V2. And again, I ask you the same question. What is the value of V1 and V2? Dun, dun, dig, 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 dig. Your chance. And you have 2 minutes to show your talents.